In this video, we're going to jump into matched samples design. So all that this is when we're dealing with two different groups, two population means, like guys and girls GPAs we've used before. When we think about that, we think about a group of sampled guys and a group of sampled girls, and we figure out the GPAs in each group. But what if there's a way to connect that? Let's say we took um, people who are dating or married, or people who are brother and sister, some way that connects one group to the other. In that particular case, we want to account for the fact that we've connected the two groups to each other. So we only did brother sister pairs. Um, the most common place you'll see this, I mean, you'll see this in things like a twin study or something like that, where we've got twins in two different groups. But the vast majority of the time you'll see this is something like a pre-post design. And that's why I kind of tongue in cheek in the last video called this very introductory longitudinal data or data over time. Time series, it's not really time series, but if you want to think about it like that, fine. It's just data over time where we've got a pre and a post. Now, why is pre-post like that? Because at the pre, let's say you and a friend of yours and another friend of yours all got recruited into Dr. Florence study. If we did a pre-post design, I might get you to take a measurement at pre, and you would all take it. And I might get you to take a measurement at post, and the same three people would take that. Now, notice how this is different than the guy and girl GPA. If I get GPA from three different guys, the GPA can't be from the three same guys who are now girls, right? I mean, we could do a study like that. In that case, that'd be a match sample because we'd have a reason to connect them. But if I just get a random sample of 50 guys and a random sample of 50 girls, there's no way to, why should one guy be connected with one girl or anything like that? There's no way to connect them. So match samples is when there's a reason to connect one group to the other. Again, the vast majority of the time, this is going to happen in something like a pre-post design, where the reason I would connect is because the same person answered the pre and the post value. Um, Now, why do we do this instead of just doing a two populations design? Or a two populations analysis when we have this matched design. And honestly, the reason we do this is that there's some variability that is considered error that we can remove. So the fact that one person tends to score higher, both pre and post, than a second person, we can remove that skill difference between people. Let's say I'm doing a pre-post on your statistics ability before and after class. And I've got three students take the pretest, and it's the same three students who take the same test at the post, and I try to see, did their scores go up? Well, maybe the first student got a really high score and it increased slightly and still got a really high score. And the second student got a really low score, but it still increased slightly, and they still got a pretty low score in the post test, but they still went up. The fact that the two students, one student has a better understanding of statistics to start with, isn't necessarily what I want to look at if I want to look at the effect of the statistics class. In fact, that would be a bad thing. That would be a confounding variable if you remember us talking briefly about those, or you remember those from your earlier stats class. Um, so that would be a variable that kind of messes with my conclusions a little bit. Or at the very least, it introduces this additional variability that is error. In this particular case, I can remove that additional variability. It's kind of like white noise on a TV. You'll hear me talk about it sometimes. So I can remove that white noise and focus just on what I want to see, which is how much did you grow? How much did you change from pre to post? So when I remove error, what does that do? Well, ultimately, it either gives me a more precise estimate if I use the same sample size, or I can use a smaller sample size if I keep the same, the same type 1 error rate. So I can either lower my type 1 error rate with the same sample size, or I can lower my sample size and keep the type 1 error rate because I have less error from removing that additional variability. So that's why we do this. That's when we do this. Match sample design. Again, we've got a bunch of cases, twin studies, husband and wife teams, etc., that we can do this. But the most common case that I'm going to use this in is something like a pre-post design, where the same person is doing the same test at pre and post. So in this particular case, we're not doing a pre-post design. We're doing different reports that we send out. So I'm going to use 2 different delivery services. And you'll see in the next slide, what I'm going to do here is I'm going to send to a whole bunch of cities. So the cities are kind of like the people in that previous case. And I'm going to see how long it takes each of these delivery companies to get to that city. So I'll have delivery company 1 and their time to the city, delivery company 2 and their time to the city. Now, why is this match samples? It's because as I go down the list of the delivery times with company 1, there is a way in which I could connect those delivery times to company 2. And the way I connect those is, well, hey, this time went to Seattle, that time went to Seattle, this time went to Denver, that time went to Denver. So because there's a reason or a way in which I can connect these, that's why this is going to be a match samples. Again, this is a harder case, and it's one of the ones I want to talk about because pre-post is really easy to identify. This is one that you may be tempted to say, okay, I've got some delivery times from company 1, delivery times from company 2. It's a 2 samples test. And again, that's not necessarily a bad thing. If you did a 2 samples test here, if you didn't know, it's better to do a 2 samples test than to try and mess up to do a match samples test. But if you can recognize, actually, there's a way in which these values are connected that is meaningful, that's going to help. All right, so how do we do this? Well, the trick as to how we calculate this is, believe it or not, we're going to use a 1 sample test. Oh my gosh, Dr. Florin, but we've got 2 different groups. Yes, we do. But often what we're looking at is the difference between them. And because we can match up the different values, so I can match up the Seattle times, the Los Angeles times, the Boston times, what I can do is I can actually calculate the difference between the times. Now, it's important that I calculate all of the differences in the correct order. So just like we had mu1 and mu2 and said you have to keep 1 before 2 always. If you do that, same thing goes on here. If you have to keep one group minusing the other group to calculate the difference between them. So instead of looking at UPX times and INTEX times, what I'm going to do is for Seattle, I'm going to look at the difference between UPX and INTEX. So in Seattle, UPX was 7 hours slower. In Los Angeles, UPX was 6 hours slower, etc. And then I'm going to do a 1 sample test on the difference. And I'm going to see, is this difference 0, indicating there's no difference between UPX and INTEX, or is this difference different than 0? So I'm going to calculate for difference. I'm going to use the notation D, and I'm going to do the exact same thing I would do in a 1 sample test. I'm just going to use the difference as my data as opposed to these 2 populations. So this is the weird but cool way in which we approached matched pairs, is instead of looking at mu1 and mu2, I'm going to look at the difference. Now I want to pause for a second, and I want you to take a deep breath. Take a deep breath. The reason I want to pause is I want to talk about why can't we take the difference in the other case, like when we have 2 populations. Why isn't this the normal way that we do it? And the reason is because, remember, in the group of guys and the group of girls, there's no way to connect any of the guys to any of the girls in a meaningful way. Here, I can connect this time to that time because they both went to Seattle. But with the guys and the girls, like, just because I selected them randomly first, that doesn't mean that there's any meaningful connection between them. So in that case, taking a difference between random guy number 1 and random girl number 1, that difference doesn't really mean anything. So I have to look at the guy as a group and the girls as a group and take the difference between those groups. That sounds a bit semantic, and it is a bit. Again, what this is doing is removing the individual city differences. Seattle is taking a lot longer than Milwaukee, but I don't really care about that. Like the fact that Seattle took longer for both companies, that's not what I really care about. What I care about is which company is more. So the fact that Seattle had a difference of 7 hours between UPX and Intex is more meaningful than the fact that Seattle on average takes 28 hours and Milwaukee on average takes 8 hours. So the reason, again, that I don't do this difference idea with the regular data is because I can't meaningfully match up each of these numbers from the UPX group with the Intex group. It'd be like if I didn't tell you any of the cities for these times, you wouldn't have a way to match them up. So we'd have to find the average of UPX and compare that to the average of Intex. In this case, because I have the additional information, I can take the difference first, and that actually is really helpful statistically. So when we are able to do this, we like to do this. We like to take the difference first. And when we're not able to do this, we don't. And that's when we use the previous situation. Sometimes you'll hear this called independent versus dependent samples. In this case, because these two are related based on the city, sometimes these are called dependent samples. And then independent samples are when there's no way that I can connect any of the numbers from the first group to the second group. So when there's a connection, I take the difference first, and then I do a one sample test on the difference. And you can go to the previous lecture for details on the one sample test. We'll walk through it quickly here. I'm going to use D instead of X to represent this isn't the original X1 or X2. What this is the differences. So I'm going to use D's. So the mean of D, I just go to the difference column and take the mean of all those. The standard deviation of D, I literally just take, again, I'm just treating this as my data set now, and just take the standard deviation in the same way I always would of these differences. And I use these two values, the point estimate for the mean and the estimate of the standard deviation, and I use these in my calculation. So typically I'm looking at, is there a difference between the two delivery services? 0 and not 0. You could make this a tailed test if you wanted to. You could say, I think UPX has a longer time, and you could make this a greater than. Again, the order of subtraction is important for which direction you want to make this, just like we talked about previously. So you want to be careful about the order of subtraction if you are using a one-tailed test. But no difference. It doesn't really matter if it's a positive or negative difference. Both would indicate rejecting the null hypothesis in a non-directional case. So I don't really have to worry as much about the order of subtraction as long as I keep it constant. In this case, I'm going to use alpha equals 0.05 level of significance. Again, pretty typical. And then I'm going to do my typical one sample test. So I've got the point estimate minus the null hypothesized value divided by the standard error, which is the standard deviation over the square root of n. So in this case, I've got 10. And again, I'm really treating the differences as the data. So in this case, my sample size isn't 20, and I do have 20 values. It's important to note. I've got 10 from UPX, I've got 10 from Intex, but I've only got 10 total, so that's 20 total, but I've only got 10 total differences, and I'm really treating the differences as the data here. So in this case, I've got 10 data points for those differences. So I've got the mean of the differences divided by the standard deviation of the differences over the square root of n, and 2.94 is my test statistic. This is a test statistic indicating the differences between those after accounting for the city. So I'm going to use critical value first. I'm going to use T because I calculated the standard deviation by hand. Degrees of freedom is 10 minus 1 of 9. Alpha is 0.05. I get my cutoff. So because I am bigger than the cutoff, and again, we would, sorry, I'm skipping over this, but remember that this is a two-tailed test. So we cut alpha in half. Alpha over 2 is the value we're comparing to. It's a two-tailed test. So I cut alpha in half. I'd be looking at being bigger than the positive value or being smaller than the negative value. Because this is a positive, I'll just go on and look at the positive. It is bigger than the positive value, so I reject that null hypothesis. And 95% confident that there's a difference in the mean delivery times of the two services. Again, this is at the population level. And, you know, just for fun, I apologize if you're getting sick of seeing this, but I do want to draw it out. This is my two-tailed test. So the shaded area at the bottom, that's my rejection region. So when I say bigger than the positive value or smaller than the negative value, this is what I mean. Is it bigger? Is it in this shaded region? Bigger than the positive value? Is it in this region? Smaller than the negative value? It's positive 2.94. So that's out here on the right-hand side. It's bigger than the positive value. All right, so how about our p-value? Well, I plug this into R, or I can look on the table. P is between 0.02 and 0.01. So in that particular case, well, again, I don't really like this. Normally I'd plug it into R, but remember, if we do plug this into R, what we have to do is to double the p-value. So actually the p-values that I found on the table were 0.005 and 0.01, and then I doubled them because it's a two-tailed test. So whatever p-value I would find in R, the distance that's more extreme than this one, so more extreme on the positive side, I'd multiply that by 2 because it's a two-tailed test, and then that would be my p-value. In this case, these were the values I found on the table, 0.005 and 0.01. I double them, so 0.01 is doubling 0.005, 0.02 is doubling 0.01. Why do I double them? Because we double the p-value in a two-tailed test. So after doubling them, I find that all of these are still less than 0.05. So I still reject the null hypothesis. And again, this means that we have evidence to indicate that there's a difference in the times for the different services. All right, so this has been our quick jump into matched samples. It's pretty cool. Again, if you have a reason to match each individual value from one group with another group, and again, think like pre-post test. The same person took the pre-test as the post-test, or in this case, delivering to cities. We delivered to the same cities in both groups. That would be a good indication that we have matched samples. And matched literally means the regular old definition of matched. Is there a reason that you can match them up? If I mixed them all up, could you draw an arrow from one to another in a meaningful way? And if the answer is yes, then you may have matched samples and you would use this approach. We like to use this approach when we have this, but we don't always have this. And again, actually, I'd say typically we don't have matched samples. It requires a little bit more information than we normally have. So we typically use the other approaches that we've been talking about in the previous videos. But when you do have a reason to match individual values from one group with individual values in another, we tend to use this approach of taking the differences, running a one sample test with the differences, typically comparing to 0, and then doing our traditional conclusions based on that one sample test. In the next video, we'll jump into tests of proportions, where we do all this for proportions. It'll probably go pretty quick because it's all going to be pretty familiar, but we'll do that in the next video.